Good morning, everyone. It's great to be here with you and get a chance to have these online sessions at the World Water Week 2023. I will discuss today with you the Leakage Emission Initiative. Established on how to establish a standard carbon balance for drinking water utilities. Apologies, I had to pause here because I had an echo on my side. So my name is Alexis Lecarco. I am Senior Director for Client Sustainability in Europe for Xylem. Xylem is a global technology and solutions suppliers aiming at resolving water challenges and building affordability in the access of water and sanitation, but also in building resilience. Feel free to reach out at any time if you have any questions during this online session in the platform chat. It is open on my screen, so I will see your questions popping up, and I'll intend to respond to them at the end of this session. So what is our problem today when it comes to water leakages? Water leakages, as we know, are a strong focus within water management. I will focus here on the next couple of slides on the European pictures, considering that it is my regions of expertise. However, the leakage emission initiatives that I discussed here today is a global initiative and can be applied across other regions. So when we look at Europe, we clearly see that we have a leakage problem. Across operation associations across Europe has published recently that we have about an average of 25% of water losses every year. And when we translate this in terms of volumetric losses, as represented on this figure, we see that despite the strong percentage, the volumetric are very important. The volumetric representations really shifts around a little bit the score among countries in Europe. And we see that Italy, UK, France, Spain, and Poland are really leading the race on water losses with massive amount. Italy with 1.7 million cubic meter Olympic size swimming pool loss per year, and so on. So you see the critical impact that we see on water losses. Why do we still have this problem today? Is a critical question, and I can list three main factors: the economics, the lack of visibility, and the diminishing returns. Economics, why? Well, because of the conservative economic level of leakages calculations. That means that it is across many regions in Europe until today, it was still more economic to keep wasting water than having to fix the leakages or replace long pipelines of network of water mains because of the expensive cost of excavations and construction. That is changing today because of the availability of freshwater resources reducing. We will head to a tipping point where replacing the network might become more economic than having to abstract more resources from the environment. Lack of visibility. Well, if you don't know what you're losing, then you can't fix it. You don't know what you can't measure easily. So having a low level of smart metering and metrology across district meter area leads to the fact that we don't know where how much leakages are within municipalities. So it is sometimes a reason for not addressing the problem. And finally, diminishing returns. It is an important commitment to go with leakage reduction. And it will take extensive amount of budget to address the old infrastructure within utilities. So it is not always straightforward to build this strategic plan around leakages. So when we look at what is the financial and environmental impact of leakages, here are at least a couple of examples. They're not exclusive or exhaustive. It might be worth extending it as well. I just wanted to make sure that we get the top 4 that come to mind. First, fixing leakages has important operation potential in avoiding expenses from excessive or extra pumping and treatments. Also, unrepaired leaks will lead to very expensive bursts of main and network that will be extremely difficult to repair, requiring a lot of civil work and closure of urban area for fixing it. There's definitely higher costs through expensive pipe replacements, and the leakages will also lead to shorter asset lives by using them on long terms. And then not to forget that a leaking network will impact the end user of utilities. Customer satisfactions will be degrading if the network leads to excessive losses that could damage urban environment and so on. The utilities' reputation might be degraded with lots of costly mediatic impacts, which should be avoided. When we look at environmental impacts, we look at, in general, giving you high-level numbers. In Europe, water and wastewater industry is responsible for about 3% of EU energy consumption. When we look at emissions, water and wastewater industry is responsible of 8% of total EU greenhouse gas emission. When we look at how much it takes of energy to produce and pump a cubic meter of drinking water, we see that it takes up to 0.4 kilowatt hour of energy. So even if we look at having renewable energy contract and so on, it is still using that much capacity of energy to produce a meter cube. And unnecessary pipeline replacement results in really massive carbon emissions through the constructions and the civil work around it. So water management and water losses have directly drastic impact on environment. When we look at emissions from an overall drinking water management system, I wanted to give you an idea of where were the main emission sources that the utilities are facing. It is not always trivial to understand within water abstractions, water treatment, and water distributions, what are the point sources of greenhouse gas emissions. So on this image that you see the graphics of abstractions from either surface water, groundwater, or desalinations, going through treatments, pumping stations, and distribution network. I highlighted the key sources of emissions from Scope 1, Scope 2, and Scope 3. What are those scopes? Those scopes are the main categories of boundaries of this specific emissions from an organization. And when we look at Scope 1, those are the direct emissions. Direct emissions are those that are generated and owned by the organizations. And in this case, for drinking water abstractions, especially from groundwater, 30% of the Scope 1 emissions come from process gas emissions emitted from the change in pH from the drinking water or the fresh water abstracted from the groundwater and emitting then CO2 and methane. It is not a number. Those numbers that I give on the screens are not like scientifically proven, but they are just case scenarios of that we've been able to witness with utilities and understanding, okay, these are proportions that we are facing in some cases across Europe. In the scope 2 indirect emissions, scope 2 are the indirect emissions, meaning emissions generated by the utility using electricity within their regions. That electricity is being produced by a certain amount of fossil fuel power, which generate emissions. And in this case, looking at across the operations of the utility, we see that 65% comes from the conveyance of the of water, 20% through treatment, and the rest on the distribution. This is excluding if we have seawater desalinations. In that case, we will boost indirect emissions by 350% due to heavy consumptions of energy in desalination. The scope 3 is the value chain emissions. That means that how much your suppliers or customers are emitting CO2 or greenhouse gases because of the business that they generate with the organization, with the utility. And in this case, productions of chemicals used in water treatment, but also the concrete and the material in new civil constructions or in the infrastructure of the water utility are generating the highest lead of emissions or the highest source of emissions within that sector. So I hope this gives you an idea of where emissions are within drinking water management. So with this picture in mind, we see that today climate change is drastically impacting the way regulations and utilities foresee the planning in the future. We have heavy extreme weather events with droughts and flooding. There is a possibility of high migrations towards regions that are in a safer zone with more access to fresh water. So in this case, what type of environment changes do we see today? Well, in 2020 in Europe, the new drinking water directive has been released. It really aimed at addressing access and quality of drinking water across Europe. And for the first time in this new revision, the directive highlights the need of assessing water leakage levels for territories and developing an improvement plan for reducing leakages. The utilities in targets are those that supply at least 10,000 meter cube per day or serve about 50,000 person equivalent. The assessment needs to be done by January 26, which means that in the next couple of years, there will be an important need of managing and assessing conditions of networks to detect leakages and so on. This is a great improvement on this directive, considering the environmental change and climates that we see around, making water resources much more scarce and increasing the values of water in its network. So we also see other big governmental initiatives. The Paris Agreement is an important one, but also across Europe, we see Fit for 55, where Europe aims at cutting emissions by 55% by 2030. And the European Climate Law, which aims at having full carbon neutrality for the regions by 2050. These are very important changes that will drive municipalities and cities to take actions, not only pushing the industrial actors in their regions to meet net zero, but also their own infrastructures, meaning power, gas, utilities, water utilities, and so on, to take actions towards reducing their emissions. So we see stakeholders engagement changes. We have C40 cities that most of you probably are familiar with, aiming at meeting the Paris Agreement by 2030. Across the world, 146 utilities have already committed to the race to net zero through the UN commitments. And then we see also EU missions for 100 climate neutral cities in Europe, which are 100 cities across different member state countries aiming at having climate neutral activities by 2030. And I engage you all to look at those commitments and engagements from stakeholders, demonstrating a clear move towards facing importance of carbon accountability. So where do you start? Because we have two big problems in hands. One is the water losses. The other one is carbon management. The water managers are facing those potential targets to meet. So where to start? Well, the leakage emission initiatives has been started as a collaborative group within IWA Water Loss Specialist Group. And I highly recommend you to check it out and Google it. If you're a member of IWA, please have a look directly at the white paper that has been published there. And I think it's accessible also to non-members. And the objective of these collaborations between IWA Water Loss specialist groups, the Alliance for Water Efficiency, and Water Research Foundations and other partners, aimed at truly establishing a standard carbon balance for drinking water utilities and incentivize them to reduce leakages and build carbon management capabilities. So the white paper at this point is a growing document, a growing place where information can be found, but it will generate future development of tools and potentially softwares that will enable this carbon balance to be done. But it truly right now raises global awareness on on water losses and the importance of accounting carbon. It provides a consistent and objective methodology based on the water balance, and I will go there in a minute. It will also encourage adoptions of best practices, enables the utility to see how important it is to develop carbon management capabilities, and then it supports the Paris Accords and other global efforts that I have just mentioned a minute ago. It all bases its development and methodology on the standard water balance that has been already well accepted in the sector. It was developed by IWA and the American Water Works Associations, and is one of the most common platforms used to identify and quantify losses in networks. It really brings together and cascades down volumetric utilizations of water from the water supplies to the authorized consumptions, all the way down to revenue water. But then highlights, I'm gonna take my laser pointer. It also enables to track down water losses among apparent and real losses to eventually calculate non-revenue water. So most of you are likely aware of these platforms. If not, I recommend you to have a look at it and the software available with it. So from there, how do we start by looking at carbon? Where do we start? Well, carbon accounting is not extremely complicated. It is actually, the complexity comes from basically conversions of units and making sure that you have the right data sources of both energy intensity and emission intensity, so that you can convert your business activity, in this case, the use or the productions of drinking water, into an equivalent emission form in terms of a carbon equivalence. So in the case of water losses, for example, we can calculate how much energy is wasted from having water losses by multiplying water loss by the utility energy intensity times also the emission intensity of that energy sources. And that emission intensity of energy sources fluctuates across all countries, because the energy grid that is being made available through energy contracts to utilities, but also to residents, depends on the mix of fossil fuel and renewable energy that have been used, or source of power, to generate that electricity in the grid. So for example, I mean, you see this list is coming, it's currently available online, either through the international energy associations, but also on Eurostat. In Europe 27, we have an emission intensity of 275 grams of CO2 equivalent per kilowatt distributed into the grid. So this basic accounting, how do we apply it to the water balance? Well, in a very similar way, and in a very similar way than what we have expressed, we look at, we need to be having handy the local emission intensity from the energy source, publicly available, the local energy tariffs, which enables also potentially to calculate systematic operating cost. And then we look at the overall utility water supply. The water supply leads to a total energy usage. That total energy usage can enable the calculations of the utility energy intensity in kilowatt hours per cubic meter. The overall water supply also enables to calculate the utility total indirect emissions, or the scope 2, linked to producing the conveyance and treatment and distributions of drinking water. Now that translates into the water loss in water balance, and then similarly you calculate the energy used or wasted through the losses, the indirect emissions linked to those losses, and the operating costs. So if we put some figures into this table, it might be a bit more speaking to you. This is a fictive water utility of serving about 500,000 person equivalent, so 500,000 PE, using energy grids from Europe 27. So similar to what I said before, 275 kilo of CO2 per kilowatts. This utility is annually supplying about 36 million cubic meter. That has energy use of 42 gigawatts hour, and has emissions of about 12 kilotons of CO2, and has operating cost linked to the use of energy of about 8.5 million euros. All this is for the water supply. When we look at how much is being wasted through the 25%, the average numbers across Europe of water losses, we see that about 9.1 million cubic meter are lost, which is equivalent to about 3,650 Olympic swimming pools. But when we look at the energy and emissions, we look at a loss or a waste of energy of 10 gigawatts or 11 gigawatts, or almost 3 kilotons of CO2 per year. If that doesn't speak to you, it's basically equivalent to almost close to 10,000 flights, emissions from 10,000 flights from Charles de Gaulle to New York City. Notably, the utility, if fixing all water losses of 25%, could also save up to 2.1 million euros annually. So this gives a bit of some figures behind, and the ability of the carbon balance standard tool to cascade down values behind water losses. Now, what does it mean when an utility aims at doing water loss reduction projects? How can it evaluate the potential benefits that it drives down on its bottom line, but also on environmental impacts based on carbon reduction? Well, I have here two case stories, one in Valencia in Spain. The Valencia municipality aimed at reducing the amount of fraud, so of non-authorized water usage, but also reduce its water losses that has been mapped up to 40% at that time in the network. The project solutions was built around adding smart metering and pressure gauges in the district meeting area, so that you can truly build the balance of water in and out of the system. The collections of the data into a smart data platform to build a hypervision of the city and the water distribution. And then finally use advanced algorithm, machine learning, and expert consultancy to basically aim at optimize the distributions, detect unauthorized usage, and also water losses. The outcome of this project is basically 18% reductions of water losses, which is equivalent to more than 4 million meter cubes of water saved annually. And when you translate that with the standard carbon balance, we look at 1.1 kiloton of CO2 reduction, which is equivalent to about 3,650 flights, again, in this case. Very significant impact and very drastically valuable in the carbon accounting of that water utility with carbon avoidances. The second case study here is an Italian case study close to Naples. The utility here has an underwater pipeline that they know losing 50 liters per second based on water balance calculation. And the objective is to eliminate that water loss. Unfortunately, the pipeline is underwater, so very difficult to replace, and requires a specific condition assessment project. The inline free swimming acoustic sensors pinpoint the leak and air pockets that without disrupting the service, and enables an inspections on relatively long distances, in this case, several pipelines for a total of about 2.5 kilometers. The outcome of the project is a strong leak detections, detections of one large leak, which was the cause mostly of that main loss of 50 liters per second. It was being repaired. The reparations led to a saving of 1.6 million cubic meter of water annually. And that is equivalent to about 453 tons of CO2 through the carbon balance calculation, equivalent to about 1,500 flights. So you see the impact that we get through using different perspectives of not only energy saving, water saving, but on top of it, the value that we bring in having carbon added to it. So on this, I close the presentations and opens to a couple of questions. If there is any, feel free to add them on the chat in the platform. I thank you very much all for attending. I have here on the screen my contacts. Feel free to take a screenshot at any time and reach out to me if you would like to have more information about the leakage initiative, the leakage emission initiatives, or even discuss some of the case stories that were presented in this presentation. Thank you very much. And I look forward to having you reaching out to me. I think it would be much easier. And I will, we can definitely discuss a bit more the calculations behind here and the database of the carbon balance. So a couple of questions regarding the carbon balance calculation. I can go back. The main calculation sources are represented here on this screen, and feel free to take a screenshot, and the recording will be available later on. The data sources are publicly available in terms of energy or emission intensity for energy, and from there, you can cascade down based on the water balance standard, the values of energy use and carbon emissions. When it comes to the energy intensity, it's specific utility by utility. And in the case of this example here, I use publicly available literature about the energy use from abstractions, treatments, and distributions in water network. But the water utility have access to their energy intensity or energy use for their operations, and that will be the number to use in the table. When it comes to control the leak and what technology to be used, I recommend to reach out to me. We can have an extended conversation on that, considering that there is multiple technology between metrology and condition assessments on top of digital solutions enabling this hypervision of a network that can be shared, but I don't think we will have the time to address that here. And thank you, Stuart, for adding in the chat the link to the leakage emission initiative group, where you will find additional information on both the calculations and the white paper that have been discussed here. On this, I will close this session and thank you all. Have a great day.